All cells need oxygen. It is the essential fuel which is necessary to enable cells to stay alive and to carry out their various activities. Bringing oxygen to the cells requires the uptake of oxygen from the air in the lungs, its transportation in the blood, and its delivery to cells all over the body. The first step is the taking up of oxygen by blood flowing through fine capillaries in the walls of the lungs' air sacs, or alveoli. The oxygen molecules change from their state as a gas freely circulating in the air, dissolving into a solution in the plasma within the capillaries of the alveoli. Once in the solution of the blood, 98% of this dissolved oxygen is taken up by passing red cells, leaving just 2% remaining in the physical solution unattached. Red cells are particularly well suited to transporting oxygen because they contain a special oxygen-binding protein known as hemoglobin. Each molecule of hemoglobin itself contains 4 molecules of heme, an iron-containing pigment, which binds oxygen loosely and reversibly. Hemoglobin that is fully saturated with oxygen is bright red and is called oxyhemoglobin. On the other hand, hemoglobin that is not saturated with oxygen is purplish blue in color and is called deoxyhemoglobin. It is heme which makes it possible for the red cells to pick up oxygen dissolved in the blood, transport it combined with hemoglobin, and release it back into the blood as oxygen in solution, ready for delivery to the various cells of the body. Hemoglobin gives up its oxygen as red cells travel through capillaries in tissues where there is a low content or partial pressure of oxygen. The partial pressure of oxygen represents the level of dissolved oxygen in plasma. As oxygen is released and again is carried in solution, the partial pressure of oxygen in the capillaries becomes greater than the partial pressure of oxygen in the surrounding tissues. This causes oxygen to move out of the capillaries into the tissues and to finally reach the cells. This graph, the oxygen dissociation curve of hemoglobin, shows why hemoglobin is particularly suited to its role in transporting oxygen. The oxygen dissociation curve demonstrates the relationship between the oxygen carried in combination with hemoglobin, the O2 saturation, and the partial pressure of oxygen in the arterial blood. The sharp upstroke and the flat plateau illustrate how oxygen is released to the tissues over a wide range of conditions. Its shape means that although the partial pressure of oxygen in the blood returning from the lungs and being pumped out by the arteries may be reduced to only 50% of the normal value, say due to lung disease or high altitude, hemoglobin will still be 85% saturated with oxygen.